Curve tracing in Cartesian coordinates. Hi friends, welcome back. In this session, we focus on sketching curves on a plane which requires some of the prerequisites discussed in the previous sessions, namely increasing and decreasing nature of functions, local maxima and minima, concavity properties and asymptotes. Given any real valued function f defined on a domain D, we know that the graph of f is defined by graph of f equal to set of all x comma f of x, where x is inside D. If the function is given in an implicit form, say f of x y equal to 0, then we define graph of f is equal to set of all x comma y, where x belongs to D, satisfying f of x y equal to 0. As graph of f is a subset of the plane R2, it can be plotted on a plane, and this process is called curve tracing. For example, the graph of f of x equal to x square minus 3x plus 4 defined on the domain D equal to 0, 1, 2 is graph of f is equal to 0, 4, 1, 2, 2, 2, which is a set consisting of only 3 ordered pairs representing 3 points on the plane. So, it can be easily plotted on xy Cartesian plane. But if the domain contains infinitely many points, so does graph of f, and thus it is not possible to plot all points on the curve as done in the previous example, where there are only 3 points. For example, consider the function f of x equal to x square minus 1 defined on the closed interval 0, 2. When x equal to 0, we have f of 0 equal to minus 1 getting a point 0, minus 1 on the curve, and when x equal to 0.5, we have f of 0.5 equal to 0.5 square minus 1, which is equal to minus 0.75 getting another point 0.5, minus 0.75. Similarly, the points like 1, 0 can be found on the graph. We have infinitely many points inside the closed interval 0, 2. So, there are infinitely many points on the graph, and hence plotting each point on the graph in real life is an impossible task. Hence, we are going to see in this session how the tools like extrema, concavity, asymptotes, etc. may be used to produce a rough idea of overall shape of the graph without computing the large collection of points required for a detailed plot. We now introduce the concept of symmetry of curves, which will reduce the work of curve tracing by half. Several symmetries are possible on the plane, of which some of them can be identified easily. If the equation does not alter when x is replaced by minus x, then we have a symmetry about y axis. In this case, graph on the left of y axis is the mirror image about y axis of the graph on the right of y axis. For example, the graph of y equal to x square is symmetrical about the y axis, as the equation y equal to x square is not altered when x is replaced by minus x. As another example, the equation y equal to 2x to the power 4 minus 3x square plus cos x plus 2 is not altered when x is replaced by minus x. Hence, its graph is symmetric about y axis. Similarly, if the equation does not alter when y is replaced by minus y, then we have a symmetry about x axis. In this case, graph that lies below the x axis is the mirror image about x axis of the graph above x axis. For example, the parabola y square equal to 4ax is symmetric about the x axis, as y square equal to 4ax is unaltered when one replaces y by minus y. Remember that this curve is not the graph of a function, as it fails vertical line test. If there is no change in the equation when both x and y are replaced by minus x and minus y respectively, then there is a symmetry about the origin. Observe that minus x comma minus y is obtained when x comma y is rotated by 180 degree. Thus, when there is a symmetry about the origin, the curve is not altered when rotated by 180 degree. Taking 180 degree rotation is equal to taking reflections first about x axis and then about y axis. Hence, when the curve is symmetric about the origin, it does not alter when reflections are made first with respect to x axis and then with respect to y axis. In this case, we can complete the graph if we know the shape in any two adjacent quadrants. For example, the hyperbola xy equal to 1 is symmetric about the origin, as when both x and y are replaced by minus x and minus y respectively, we get minus x into minus y equal to 1, that is xy is equal to 1, the same equation. Finally, if when x and y are interchanged, the equation of the curve remains unchanged, then the curve is symmetric about the line y equal to x. For example, x cube plus y cube equal to 8xy is symmetric about the line y equal to x. In fact, interchanging x and y, the equation changes to y cube plus x cube equal to 8yx, which is same as the original equation. Now, let us move on to sketching curves. The general procedure of curve sketching can be given as: step 1, identify the symmetries. Step 2, plot specific points such as x intercepts, y intercepts, points of local extrema and inflection as and when they are obtained. Step 3, identify asymptotes. Step 4, find y dash and y double dash. Step 5, find local extrema and points of inflection. Step 6, find the rise and fall of the curve using y dash. Step 7, determine the concavity of the curve using y double dash. Step 8, make a summary and sketch the curve. We may improvise these steps according to the problem. Let us start sketching with a simple function y equal to x to the power 4 minus 2x square plus 2. When x is replaced by minus x, we get y is equal to minus x to the power 4 minus 2 times minus x square plus 2, that is y is equal to x to the power 4 minus 2x square plus 2, the same equation. Hence, we have a symmetry about the y axis. Hence, we plot the curve only for x greater than or equal to 0, and making use of the benefit of symmetry, we make a reflection about y axis finally to complete the work. When x is equal to 0, we get y is equal to 2. Thus, 0 comma 2 is the only one y intercept. Further, y equal to x to the power 4 minus 2x square plus 2 is equal to x square minus 1 whole square plus 1, which is always positive. Hence, the curve never intersects the x axis. As we have a polynomial function, no asymptotes exist. Let us now move on to the derivatives. We have y is equal to x to the power 4 minus 2x square plus 2, thus y dash is equal to 4x cube minus 4x, and y double dash is equal to 12x square minus 4. Y dash is equal to 0 implies 4x into x square minus 1 is equal to 0, so that x is equal to minus 1, 0 or plus 1 are local extrema. When x is equal to 0, y is equal to 2 and f double dash of 0 is minus 4. Hence, 0 comma 2 is a point of local maxima. When x is equal to 1, y is equal to 1 and f double dash of 1 is equal to 8. Hence, 1 comma 1 is a point of local minima. We shall now analyze the rise and fall of the curves in the interval 0 comma 1 and 1 comma infinity. In the interval 0 comma 1, x is positive, x square minus 1 is negative, and hence y dash is equal to 4x into x square minus 1 is negative. Thus, y is decreasing. In the interval 1 to infinity, x is positive, x square minus 1 is positive, so that y dash is equal to 4x into x square minus 1 is positive. Thus, y is increasing. Now, y double dash is equal to 12x square minus 4 is negative if and only if 3x square minus 1 is negative, which is true if and only if x square is less than 1 by 3. Hence, the curve is concave downwards if x square is less than 1 by 3, that is when x is inside the open interval minus 1 by root 3 comma 1 by root 3 and concave upwards in other intervals. When x is equal to 1 by root 3, we get y is equal to 13 by 9, thus getting the inflection point 0.577 comma 1.44. We have completed sketching to the right side of y axis. We can complete our work just by taking a reflection about the y axis. Let us now look at another function y equal to x cube minus 3x. When x and y are replaced by minus x and minus y, we obtain minus y is equal to minus x whole cube minus 3 times minus x, that is minus y is equal to minus of x cube minus 3x, that is y is equal to x cube minus 3x. As the equation is not altered, the curve has a symmetry about the origin. Hence, we plot the curve only for x greater than or equal to 0, and making use of the benefit of symmetry, finally we take a reflection about the origin to complete the work. When x is equal to 0, we get y is equal to 0. So, the curve passes through the origin. Further, y is equal to 0 implies x into x square minus 3 is equal to 0. Thus, x is equal to minus root 3 comma 0 comma root 3 are the x intercepts. As we have a polynomial function, no asymptotes are possible. Let us now move on to the derivatives. We have y is equal to x cube minus 3x, thus y dash is equal to 3x square minus 3 and y double dash is equal to 6x. Y dash is equal to 0 implies 3 times x square minus 1 is equal to 0, so that x is equal to plus or minus 1 are local extrema. When x is equal to 1, y is equal to minus 2 and f double dash of 1 is equal to 6. Hence, 1 comma minus 2 is a point of local minima. We shall now analyze the rise and fall of the curves in the interval minus 1 comma 1 and 1 to infinity. In the interval minus 1 to 1, x minus 1 is negative, x plus 1 is positive. Hence, y dash is equal to 3 times x minus 1 into x plus 1 is negative, and hence y is decreasing. In the interval 1 to infinity, x minus 1 is positive, x plus 1 is positive, so that y dash is equal to 3 times x minus 1 into x plus 1 is positive, and hence y is increasing. Now, y double dash is equal to 6x is negative for x less than 0 and hence is concave downwards. Further, y double dash is equal to 6x is positive for x greater than 0 and hence is concave upwards. Thus, x equal to 0 is a point of inflection. We have completed sketching to the right side of y axis. We can complete our work by just taking a reflection about the origin. This could be done in two ways, either by rotating the portion of the curve already obtained by an angle of 180 degree, or by taking two reflections, first about y axis followed by a reflection about x axis. We shall now sketch another polynomial function y is equal to x to the power 4 minus 4x cube plus 12. We do not observe any symmetries or asymptotes, so we move on to derivatives. Y dash is equal to 4x cube minus 12x square and y double dash is equal to 12x square minus 24x. Y dash is equal to 0 implies 4x square into x minus 3 is equal to 0, so that x is equal to 0 or 3 are local extrema. When x is equal to 0, y is equal to 12, and when x is equal to 3, y is equal to 3 power 4 minus 4 into 3 cube plus 12 is equal to 81 minus 108 plus 12, which is equal to minus 15. Plot these points 0 comma 12 and 3 comma minus 15. At x is equal to 3, we get y double dash is equal to 12 into 3 square minus 24 into 3, which is equal to 108 minus 72 equal to 36, which is positive. So that x is equal to 3 is a local minimum. However, at x is equal to 0, y double dash is equal to 0, and hence we cannot draw the conclusion whether x is equal to 0 is a local maxima or minima. Let us now analyze the rise and fall of the curve in the interval minus infinity to 0, 0 to 3 and 3 to infinity. In the interval minus infinity to 0, x minus 3 is negative, hence y dash is equal to 4 times x square into x minus 3 is negative, and hence y is decreasing. In the interval 0 to 3, x minus 3 is negative, y dash is equal to 4 x square into x minus 3 is negative, and hence y is decreasing. In the interval 3 to infinity, x minus 3 is positive, y dash is equal to 4 x square into x minus 3 is positive, so that y is increasing. Now, y double dash is equal to 0 implies 12 x into x minus 2 is equal to 0. So that x is equal to 0, 2 are possible inflection points. When x is equal to 2, y is equal to 2 power 4 minus 4 into 2 cube plus 12, which is equal to 16 minus 32 plus 12, which is equal to minus 4. Plot this point 2 comma minus 4. We now look at the concavity properties of the curve in the intervals minus infinity to 0, 0 to 2 and 2 to infinity. In the interval minus infinity to 0, x is negative, x minus 2 is negative, and hence y double dash is equal to 12 x into x minus 2 is positive, hence y is concave upwards. In the interval 0 to 2, x is positive, x minus 2 is negative, and hence y double dash is equal to 12 x into x minus 2 is negative, so that y is concave downwards. In the interval 2 to infinity, x is positive, x minus 2 is positive, and hence y double dash is equal to 12 x into x minus 2 is positive, and hence y is concave upwards. Thus, it is assured that x is equal to 0, 2 are points of inflection. This completes the task of sketching y is equal to x power 4 minus 4x cube plus 12. Let us now sketch the graph of the rational function y is equal to x cube minus 2x whole divided by 2 times x square minus 5. When we replace x and y with minus x and minus y respectively, we obtain minus y is equal to minus x whole cube minus 2 times minus x whole divided by 2 times minus x square minus 5, that is minus y is equal to minus of x cube minus 2x whole divided by 2 times x square minus 5. We have the equation y is equal to x cube minus 2x whole divided by 2 into x square minus 5, which is not altered when x and y are replaced by minus x and minus y. Hence, the graph is symmetric about the origin. Thus, we first trace the curve for x greater than or equal to 0 and finally extend it to x less than 0 by taking reflection about the origin. When x is equal to 0, we have y is equal to 0, hence the curve passes through the origin 0, 0. Now, limit x going to root 5 minus y equal to limit x going to root 5 minus x cube minus 2x whole divided by 2 times x square minus 5, which is equal to minus infinity, and limit x going to root 5 plus y equal to limit x going to root 5 plus x cube minus 2x whole divided by 2 times x square minus 5, which is equal to plus infinity. Hence, x is equal to root 5 is an asymptote. Similarly, limit x going to minus root 5 plus y equal to limit x going to minus root 5 minus x cube minus 2x whole divided by 2 times x square minus 5, which is equal to minus infinity, and limit x going to minus root 5 plus y equal to limit x going to minus root 5 plus x cube minus 2x by 2 times x square minus 5, which is equal to plus infinity. Hence, x is equal to minus root 5 is also an asymptote. Further, we have actual division by 2 times x square minus 5 gives y equal to x cube minus 2x by 2 times x square minus 5 is equal to x by 2 plus 3x whole divided by 2 times x square minus 5. Now, limit x going to plus or minus infinity, 3x by 2 times x square minus 5 is equal to limit x going to plus or minus infinity 3 by 2 times x minus 5 by x, which is equal to 0. So, that y is equal to x by 2 is an asymptote. We have f of x is equal to x cube minus 2x whole divided by 2 times x square minus 5. By the quotient rule of differentiation, we get f dash of x is equal to x to the power 4 minus 13 x square plus 10 whole divided by 2 times x square minus 5 square. Now, f dash of x is equal to 0 implies x to the power 4 minus 13 x square plus 10 is equal to 0, which gives x square is equal to 13 plus or minus square root of 13 square minus 4 into 10 whole divided by 2, which is approximately equal to 0.82 and 12.18. Thus, we have x is equal to plus or minus 0.906, plus or minus 3.49 are local extrema. When x is equal to 0.906, we get y is equal to 0.128 to get the point 0.906, 0.128. When x is equal to 3.49, we get y is equal to 2.474 to get the point 3.49, 2.474. We plot these 2 points. Let us now analyze the rise and fall of the curve in the open intervals minus 0.906 to 0.906, 0.906 to 3.49 and 3.49 to infinity. We have f dash of x is equal to x to the power 4 minus 13 x square plus 10 whole divided by 2 times x square minus 5 square. This function is continuous for all x not equal to plus or minus root 5, and the derivative is 0 at x is equal to plus or minus 0.906 and plus or minus 3.49. Hence, by an application of the intermediate value theorem, f dash of x does not change the sign in each of the intervals minus 0.906 to 0.906, 0.906 to root 5, root 5 to 3.49 and 3.49 to infinity. In the interval minus 0.906 to 0.906, f dash of 0 is 10 by 50, which is positive, and hence f dash of x is positive, and hence y is increasing. In the interval 0.906 to root 5, f dash of 2 is minus 26 by 2, which is negative, and hence f dash of x is negative, and hence y is decreasing. In the interval root 5 to 3.49, f dash of 3 is minus 26 by 32, which is negative, and hence f dash of x is negative, and hence y is decreasing. And in the interval 3.49 to infinity, f dash of 4 is 58 by 2 into 121 square, which is positive, and hence y is increasing. We shall now evaluate second derivative. Differentiating f dash of x is equal to x to the power 4 minus 13 x square plus 10 whole divided by 2 times x square minus 5 square, we get f double dash of x is equal to 3 x into x square plus 15 whole divided by x square minus 5 whole to the power 3. Y double dash is equal to 0 implies x is equal to 0. Hence, x is equal to 0 is possibly a point of inflection. In the interval minus root 5 to 0, x is negative, x square minus 5 whole to the power 3 is negative. So, that y double dash is equal to 3x into x square plus 15 whole divided by x square minus 5 whole to the power 3 is positive. So, that y is concave upwards. In the interval 0 to root 5, x is positive, x square minus 5 whole to the power 3 is negative, and hence y double dash is equal to 3x into x square plus 15 whole divided by x square minus 5 whole to the power 3 is negative, and hence y is concave downwards. In the interval root 5 to infinity, x is positive, x square minus 5 whole to the power 3 is positive, and hence y double dash is equal to 3x into x square plus 15 whole divided by x square minus 5 whole to the power 3 is positive, and hence y is concave upwards. Hence, it is clear that x equal to 0 is a point of inflection. We have completed sketching to the right side of y axis. As the curve is symmetric about the origin, we can complete our work by just taking a reflection about the origin, which is done by taking a reflection about the y axis followed by a reflection about the x axis. This completes the sketching of the graph of f of x equal to x cube minus 2x whole divided by 2 times x square minus 5. As a final example, let us look at a curve which is not expressed in an explicit form y equal to f of x, instead may be given by an implicit function of the type f of x y is equal to 0. The procedure to sketch the curve may not be the same when the function representing the curve is in implicit form. For example, consider the curve given by the equation y square into a plus x is equal to x square into a minus x, where a is strictly positive. The equation is not altered when y is replaced by minus y, and hence the curve is symmetric about the x axis. Let us first find the intercepts. When x is equal to 0, we get y is equal to 0, and hence 0, 0 is the only point where the curve intersects y axis. Further, y is equal to 0 implies x square into a minus x is equal to 0, and thus getting x intercepts x is equal to 0 and x is equal to a. We have y square is equal to x square into a minus x whole divided by x plus a for x not equal to minus a. Thus, limit x go into minus a plus y square is equal to limit x go into minus a plus x square into a minus x whole divided by a plus x, which is plus infinity. Hence, x is equal to minus a is an asymptote. If x is less than minus a, then the equation y square into a plus x equal to x square into a minus x never holds. In fact, for x less than minus a, the RHS is positive and the LHS is not. Similarly, if x is greater than a, then the RHS is negative and the LHS is not. Thus, x must lie between minus a and plus a, and hence we need to sketch the curve only for minus a less than x less than a. We have y is equal to plus or minus square root of x square into a minus x divided by x plus a. Since the curve is symmetric about the x axis, we look at the curve for y greater than or equal to 0. So, let y is equal to square root of x square into a minus x divided by x plus a. Then by quotient rule of differentiation, y dash is equal to plus or minus x square plus a x minus a square whole divided by a minus x to the power half into x plus a to the power 3 by 2. Y dash is equal to 0 implies x square plus a x minus a square is equal to 0, which gives x is equal to minus a plus or minus square root of a square plus 4 into a square whole divided by 2, which is equal to a into minus 1 plus or minus square root of 5 whole divided by 2. Since x is greater than minus a, we have x is equal to a into square root of 5 minus 1 whole divided by 2, which is approximately equal to 0.618 times a. When x is equal to 0.618 times a, we have y is equal to 0.3 times a. As the function y is equal to square root of x square into a minus x divided by x plus a is differentiable on 0 to a, and x is equal to 0.618 times a is the only one local extremum on the interval 0 to a, x is equal to 0.618 times a must be a local maximum. At x is equal to 0, we have y dash is equal to plus or minus 1, thus getting two tangents y is equal to plus or minus x at x is equal to 0. At x is equal to a, the denominator of y dash is equal to plus or minus x square plus a x minus a square whole divided by a minus x to the power half into x plus a to the power 3 by 2 goes to 0, thus getting a vertical tangent at x is equal to a. We may now complete sketching the curve above x axis and taking a reflection about the x axis complete the task. Okay friends, in this session we have covered most of the techniques of curve tracing. Hope you have enjoyed the session. See you next time. Have a great day.